Hello everyone, I'm Minkyu at the School of Electrical Engineering in KAIST. From now, I will talk about the integrated circuits and microsystems for next generation medical devices. Let me start my presentation with answering this question. Why do we need the integrated circuits and microsystems for biomedical applications? In current medical services and systems, we can find quite many unmet needs and problems. They include the healthcare crisis expected due to the aging population, the request for preventive care and early detection of diseases, long-term management of chronic diseases, better or less compromised quality of patients' life, lower price for affordability, less invasiveness involved in surgical procedures leading to less morbidity, and also the need for more innovative, life-changing, and saving medical devices. As the solutions to address such unmet needs and requirements, we are trying to develop this system for healthcare at home and in daily life, miniaturized medical devices, and new treatment methods and procedures. To enable these future solutions, one of key technologies we need is the semiconductor integrated circuit technology and microsystems based on integrated circuits. The biomedical integrated circuits and microsystems enable the future solutions by providing four very important advantages, namely high energy efficiency, integration and miniaturization, seamless connectivity, and embedded intelligence. These four critical benefits cannot be realized without using the integrated circuits and microsystems. So we can conclude that the biomedical circuits and systems are the key enabler of the future medical solutions that can satisfy the unmet needs of current medical services and systems. Now, let's discuss the development direction of medical electronics. We can find two obvious and important development trends in this field. One is the evolution of the energy source, and the other is the diversification of the physical platform. The primary battery has widely been used for most of traditional medical devices. Then it has been evolved to the rechargeable secondary battery, and wireless charging has been also introduced. Further, energy harvesting is being considered as the next generation powering method. Through this evolution, the lifetime of medical devices can be extended. However, if we look at the energy density of these energy sources, when it evolves from primary battery to secondary battery, to wireless charging, and to energy harvesting, the available energy density becomes lower and lower. It means that for the same volume of the energy source, we get only a much smaller amount of energy to operate the device. Looking at the other trend, the physical platform of the medical devices is being diversified. Most of implantable medical devices, including pacemakers, implantable cardiovascular defibrillators, and deep brain stimulators, have been based on this titanium can. This popular physical platform offers proven biocompatibility and hermeticity with a quite small size as well. Recently, various new physical platforms are being developed and introduced. They include insertable and injectable devices, minimally invasive surgical tools, contact lens, intracranial implants, and retinal implants. In this trend of physical platform diversification, we can also find that the device form factor is being decreased significantly to reduce the invasiveness and improve patient safety. We can make the device physically small without extreme difficulties by using our integrated circuit technology, because it is very good for integration and miniaturization. However, the real challenge of form factor reduction is with the limited space for the energy source, because a dominant portion of the device volume is occupied by the energy source in fact. When this volume reduction of the energy source is combined with the reduction of the energy density that we observed from the trend of energy source evolution, the problem of energy constraint becomes even more serious. So we can say that these two trends are closely interrelated, and as a result, the available amount of energy will be extremely scaled down in the future medical devices. In line with this development trend, we can think of two ambitious visions where the semiconductor integrated circuit technology plays a critical role. One is the bioelectronic medicine, and the other is the brain-machine interface. Let's look at the vision of bioelectronic medicine first. If we can downscale the size of medical devices to sub-millimeter cube and the power consumption to sub-100 nanowatt, the extremely miniaturized implantable devices can be attached to individual peripheral nerves. Then the device attached to the nerve will analyze and modulate neural signaling patterns to bring about therapeutic effects targeted at a single function of a specific organ. Once the vision of bioelectronic medicine or electroceuticals is realized, it will replace the traditional medicine market based on biochemicals, especially in the neuromedicine market, by providing higher effectiveness and less side effects. The other bold vision that I want to address is the brain-machine interface. There have been continuous efforts to demystify human intelligence and brain connectivities. However, it is an extremely challenging goal, considering that the human brain consists of about 100 billion neurons and 100 trillion synapses. Over the last 5 decades, progress in neural recoding techniques has allowed the number of simultaneously recorded neurons to double approximately every 7 years. Although it shows an exponential growth, mimicking Moore's law in semiconductor industry, the slope of growth is rather slow. In the semiconductor technology, the number of transistors integrated into a single chip doubles every 2 or 2.5 years. But here in the Moore's law in neuroscience, the doubling time is much longer, say about 7.4 years. If we keep this pace of development, it will take 200 more years to cover the full human brain. So many researchers are trying to introduce more disruptive and groundbreaking technologies to this field so that the slope of growth itself can be significantly modified. Through such efforts, many researchers in this field believe that the vision of seamless brain-machine interface will be realized eventually. Once realized, the powerful computing machine will become an associated part of our brain, allowing us to go beyond the inherent limit of human intelligence. Importantly, we need to note that the integrated circuit and microsystem technology will be at the heart of future brain-machine interface systems. Now let me explain how the biomedical IC and microsystem platform is constructed. In this microsystem, the biomedical IC works with various types of sensors and actuators, energy sources, and communication devices. Looking into the biomedical IC, the sensor and actuator interface circuits perform the interaction with sensors and actuators in analog domain. Then, this analog information is converted to digital data by data converter circuits. And converted data is then processed by digital signal processing circuits. The useful information extracted by signal processing is now communicated wirelessly through the wireless transceiver circuits operating in conjunction with communication devices like miniaturized antenna and microcoil. The energy delivery and measurement circuits operate with energy sources such as battery, wireless charging coil, and energy harvester to support the energy required for microsystem operation. Microsystem integration technology is another very important element to implement miniaturized and biocompatible microsystem. This biomedical microsystem based on the biomedical IC can be used for various medical applications, such as implantable medical devices, minimally invasive surgical operation, wireless health monitoring, and point-of-care diagnosis. In our lab, we develop integrated circuits and microsystems mainly for biomedical applications. to construct the microsystem platform based on our integrated circuits, we collaborate with the experts in other fields, such as sensors and actuators, energy sources, micro antenna and coils, and packaging and assembly. In addition to the medical applications, we also apply our technology to wireless sensor nodes for Internet of Things and next generation mobile devices such as wearables. This slide summarizes the ICs and microsystems we are developing for emerging smart medical device platform. We are working on the smart contact lens platform for glucose monitoring, intraocular pressure sensing, and drug delivery. We are also developing the ingestible capsule platform that performs high-resolution optical and ultrasound imaging, gas sensing, and biochemical sensing. The artificial joint platform provides the smart functions such as wear-out monitoring, pressure sensing, and biochemical sensing, as well as device identification and tracking. We are putting our major efforts to develop the intracranial device platform that enable multi-channel bidirectional interface and multimodal neural recording and stimulation. Also, our research for extreme power reduction and miniaturization will contribute to enabling the future bioelectronic medicine. The bionic arm equipped with multi-channel bidirectional peripheral nerve interface, high-efficiency wireless power link, and high-speed low-power data link is another platform that our lab is working on. From now, I will introduce some recent research results from our impact lab. This slide shows the multi-channel electrical neural recording ICs and modules that we developed recently. Using the developed microsystem, we conducted in vivo experiment using rat models. It shows the electrical neural signals recorded from the brain of a rat. It is the neural signal waveform measured from the peripheral nerve of a rat. We are also working toward more advanced neural recording ICs and microsystems that can achieve extreme scalability and multimodality, as well as higher recording fidelity and robustness based on wide dynamic range and high input impedance. This slide presents multimodal neural recording that can measure both the electric neural signals and calcium ions released by the activated neurons. By using genetically encoded calcium probes that are attached only to the target type of neuronal cells, we can conduct a cell type specific study in the heterogeneous neuronal cell populations. When the released calcium ions are combined with the calcium probes, fluorescence lights are emitted. So we can sense the presence and concentration of calcium ions by using photodiodes and interface circuits that read out the output current from the photodiodes. The implemented multimodal neural recording IC is shown here. It includes 16-channel electrical neural recording circuits and 4-channel fluorescence recording circuits. Using the developed IC, in vivo experiment has been performed. We could measure both the electrical signal and fluorescence light from the mouse brain. The next result that I want to share with you is the body channel communication IC. It was developed especially for the bionic arm platform that require high data rate and low power consumption, in addition to the detachability, robustness, and human body safety. It shows the microphotographs of the fabricated transmitter chip and receiver chip. We could achieve a very high data rate of 100 Mbps per second while consuming a transmission power lower than 1 milliwatt. Using the implemented body channel communication ICs and modules, we conducted an in vitro measurement with a porcine leg successfully. This short video shows our test results. Next, I'd like to introduce our wireless power and data link IC development result. It was developed for next generation neural prostheses like cochlear implants and retinal implants. These devices transfer the power and data simultaneously using a single pair of coupling coils. To enable more advanced features for such devices, it is essential to obtain high power transfer efficiency and high data rate at the same time. However, the traditional method failed to do so due to the strong trade-off between the power transfer efficiency and data rate. So we developed new ICs based on frequency splitting phenomenon observed at tightly coupled coils, and it could break this trade-off. This slide shows the overall architecture of developed ICs and systems for simultaneous wireless power and data transfer. Here you can find the micrographs of the fabricated IC chipset consisting of one IC for the external transmitter and the other IC for the implantable receiver. We could achieve the highest FOMs ever reported for both data and power transfer links. This slide shows the in vivo experiment setup using a forcing head that was used to mimic the condition of actual applications. Full link characteristics were measured in both through air condition and in vitro setup. We could achieve very high power transfer efficiency as well as sufficient power delivered to the load. In terms of communication capability, we could verify the successful operation at the data transmission rate of 2.5 Mbps per second. Recently, we also developed the ultrasound transducer driver having extremely high energy efficiency. It was developed for ultrasound imaging capsule endoscopy that badly requires high energy efficiency to take a sufficient number of ultrasonic image frames while operating with a very tiny battery fitting inside the ingestible capsule. This is the overall simplified circuit diagram of the developed ultrasound pulsar IC. This new circuit structure replenishes a major portion of the energy used for driving the ultrasound transducer. As a result, it can achieve a very high energy efficiency. This result shows the power consumption of the developed pulsar IC in comparison with the power consumed by the conventional Class D pulsars. We can find that the power consumption can be reduced by a factor of 4, especially at high capacitance and high voltage conditions. Looking at the ultrasound pulse echo experiment result, the proposed pulsar IC achieved the same performance as the conventional Class D pulsar while consuming a lot lower power and energy. This slide shows a selected set of IC chips we have developed over the past years. We are also working very closely with our industry partners so that the ICs and microsystems we develop can be applied to the actual medical devices. Here I'm showing a couple of development examples, such as cochlear implants, ultrasound imaging capsules, subcutaneous continuous glucose monitoring systems, and smart hip implants. These photos show our lab members, who are the people making all these things happen. Thank you very much for your kind attention. Thank you.